Perfect. So it's good to be here. It's good to see so many folks from PyHub.dev again, and so many more people that I haven't had a chance of meeting. So I have to start with an apology. I was sick since last Wednesday and only got better basically in the last 2 days, but had to travel here to Toulouse in Europe. So basically, those slides are really not what I wanted them to be. And if I'm brutally honest, I put them together from other slides in 2 hours while in transit in Frankfurt Airport. So it feels really bad to go after slides as polished as Luigi's, which was a really, really nice talk, even though I only caught the last bit of it because I just arrived here in my hotel room. But I hope there's still some interesting bits in there for some people, and we can also discuss. Well, and also to be fair, I told Matthew that I wanted to cancel yesterday night, and he told me to just run with what I have. So if you don't like it, then you know who to blame, and that's Matthew. Starting with the title of the talk, that should have been Tracking with Graph Neural Networks. There's various people who have been working on this. I'm more or less focused on one approach called object condensation tracking that I've been working on intensely throughout the last year. That was started by Gage, who's here on the right. And I more or less took over sometime last year while Gage was wrapping up his PhD. So you can, by the way, stalk us at our GitHub handles if you want. All right, there's 2 big chunks of this talk. There's talking about tracking and our approach in making this a machine learning task, and a second half that talks a bit more generally about machine learning frameworks and lessons that I've learned, frameworks that I'm using at the moment to make life easier. And I hope that this can also be applied to other projects. So starting with what is tracking, it's basically this journey from left to right shown here. So you start with a big point cloud. Those are just the hits in a detector. Every time a charged particle passes a detector layer, you see something there, which is symbolized by a gray point here. And when you say you do tracking, you basically want to determine categories. You want to bisect all of these points into groups that belong to one particle that passed through it. So in some sense, you can think of it as a labeling problem. And also you're dealing with noise as in hits that don't really correspond to any particle. So here we would have like the yellow, blue, green, red particle. Subtlety that we ignore is that in principle, you can also have one hit that belongs to tracks that intersect. Now, the difficulty here is that you really just have a point cloud. You don't have time resolution, as it would be easy, but it's really just everything everywhere all at once. Now, to make this a machine learning task, I think one of the first approaches, and also to date, one of the most successful ones, but it's not ours, was to approach this as an edge classification task. And there, the idea is you start with that point cloud here on the left, and then you start with some preliminary edge construction. And you want to connect hits or these points that belong to the same track. But at this point, you only have the coordinates, so you really don't have such a good way of doing that. So one way to do that would be just, for example, geometric constraints, because you know that tracks kind of move like inward to outward, and they don't do anything crazy. So you could start to just apply some geometric cuts on that and just draw a bunch of edges. Or you could do what's called a module map. You basically run through one part of your data or one part of your Monte Carlo, and you look at all the true tracks and see which points, which submodules of the detector are often belonging to the same track. So you kind of know what connections are possible at all, and you build all of these. Or there's a more interesting way using machine learning and embedding, we're talking about later. But anyway, at this point, you have this initial graph. And now what you do is you apply an edge classifier network to it. So that can be a graph neural network. It can also just be a plain neural network that takes in only the edge and 2 node attributes. But you look at one edge at a time, and you assign it an output probability. That's higher if it's 2 hits belonging to the same particle, and lower if it's, for example, a noise hit or 2 hits not belonging to the same particle. And then what you can do, like the easiest way to get tracks from that would be just decide on a threshold. So you throw away all of the edges of a low output classifier output. So those would be the ones with like the less bold edges here. And you could just consider every connected component of this resulting graph as a separate graph. That's not really the most optimal way to do it, but it can work just fine if your edge classifier is good. There's also more advanced things like graph walking, where you do some more probabilistic analysis of how to traverse this graph. But anyway, you can make some decisions based on the edge classifier output. And then usually, even if most of your tracking is done by machine learning, you still want to do a clean fit of every single track. So you now know or have determined what hits you think belong to the same track. And now you do a classical fit through it. Now, there should have been a slide about why we want to apply machine learning to this at all. So I'm just gonna do it verbally here. So the reason is with high luminosity LHC, the number of collisions and the number of pileup in the detector will be much higher than it is today. And most of the classical algorithms, for example, combinatorial Kalman filters, scale with n squared for that. So they just become pretty slow the more noisy, the more busy the environment in the detector goes. And there's some hope that neural networks can scale almost linearly. So Exatracks, who've been pioneering this tracking as an edge classifying task, they also show some plots where you can see almost linear scaling with pileup. So that's the hope there. But at the same time, there's a lot of other teams working also on non-machine learning solutions that also, of course, have improved scaling by now. So it's by no means the only way to do this. All right. So this was tracking as an edge classification task. Let's quickly talk about graph neural networks. It's the only kind of theory slide on this in the slide deck. I just want to show for people who don't know it that graph neural networks are pretty simple in principle. So the input to a graph neural network is a graph. So you have nodes and you have edges, and nodes have node features and edges have edge features. And usually what a graph neural network does is, or at least in our case, it takes the input graph, maybe there will be some latent graphs, but in the end there will be an output graph that has the exact same structure. So the same edges, the same nodes, but it will have re-embedded node features and edge features. So like these X's and M's will be different. And the way this is done is that you calculate new messages for the edges simply based on the old message and the 2 node features. And for the new node features, you take the old node feature and then you aggregate over all of the messages. And that's being put into another just normal neural network. And this aggregation is permutation invariant, so that, like depending on in which order the edges come, it doesn't make a difference. So basically, it's just a normal neural network with this additional neighborhood aggregation that kind of lifts this normal neural network to a graph structure. But the graph structure is not changed by the graph neural network. So in the edge classification, then in the end, for example, like this message would just be, for example, a single number for the output probability. All right. Now let's talk about the strategy that Gage and me have been exploring, and Gage really has started, because our work's different than edge classification, and I think it's a really nice idea. So there we again start with the point cloud, but this time this is a very high level explanation here. Rather than considering the edges to be already representing something about the physical tracks, we instead operate on a latent space, and we simply throw all of these points one by one in a latent space, and we shape this latent space by repulsive and attractive loss functions that we use to train the network in such a way that when we do this embedding of the point cloud into the latent space, the points that belong to the same particles come very close together. So for example, you could use something like eta, for example, that would already kind of help you to achieve that. And once you've achieved that, and you already have like this cluster forming without you knowing exactly already the particle assigning in the first step, you can collect them rather trivially with something like db scan. So the trick really here is this repulsive and attractive loss in the training of the network. There's some cool other approach other than this one from Daniel called influencer loss that he got inspired from Twitter by. But here there's only one kind of detail in that these repulsive and attractive potentials are always relative to what we call a condensation point, which is one special point among all the hits of the same particle that's also assigned by a learned neural network. And that can be useful to have like a special point in each cluster to represent the whole track, because you can have it learn track parameters like PT, or at least that's what we hope. And there's also a team with Lieret working on using that at Bell 2, who definitely got the track parameter prediction working. So we hope to also apply that to high luminosity LHC situations. So quick zoom in on training losses, and then we're going to get more technical. Let's just talk about attractive loss function and repulsive loss functions, and forget about the condensation points for a second. Basically, we're doing training, so we know the truth labels of all of these hits, and the attractive loss function rewards hits, for example, of the blue particle to get close to the condensation point of the blue particle. So those all kind of attract. And then we have a counterpart to the repulsive loss function, where if you, for example, have a green particle, then it's repelled from the blue condensation point. So these attractive and repulsive losses are always relative to one of these condensation points, but they are kind of antagonizing forces that hopefully result in this clustering. In fact, you can also do the whole thing without talking about condensation points and just pick pairs of these points, and that also works. And let's not get into the details. Let me skip this one and go to this pipeline. This is what we currently do, and I think this is really the last slide on kind of the layout of our pipeline and all the machine learning background. So here what we do, we have basically two big stages. We start with the point cloud, and this is the third graph construction algorithm that I was mentioning. And we already do something similar to the object condensation in the first step. We have just a fully connected neural network taking every point by itself, putting it in the latent space, again, being trained with repulsive and attractive potentials in such a way that the hits from the same particle get close together. And then we just do k-nearest neighbors to construct a first graph. So this first part works without ever having a graph. So it also doesn't work perfectly or anything, because you only have the coordinates and any other information that's attached to the hits, for example, cluster shapes and so on. But it's good enough to get a pretty good graph where you reasonably connect all hits from the same particle. And then we have the actual graph neural network that kind of picks up from where this left. So it picks up from this latent space, and leveraging message passing across these edges brings hits from the same particle even closer together. And finally, we collect the clusters with dbScan, which is just a off-the-shelf clustering algorithm that doesn't have any learned parameters. So if you're more interested in the results and details about physics performance, there's a talk I'm giving tomorrow at Connecting the Dots, which is a workshop here in Toulouse, where we'll have some numbers. Also, the previous pipeline that I just skipped, we just put a archive preprint on it, which also has some details about what you're doing. I should also mention that this first stage, graph construction with metric learning, was, I think, invented by or applied to this purpose for the first time by the Exatracks group, who are doing a really good job. All right, so let's talk tech stack and a few lessons learned. So first off, this is implemented using PyTorch and PyTorch geometric for the graph neural network part. And so a very simple way to initialize or to build a graph neural network shown here on the right. So if you're familiar with PyTorch, this probably also looks familiar. So there's an initialization method where you set up layers, and then a forward method where you take an input vector or input tensor and pass it to all of these layers until you get something out. So here we have, okay, so it's not applied to an edge classification thing here, but it's just a general example. And you see here that we take kind of off-the-shelf GNN layers directly from PyTorch geometric. This one is called GCN conf. So PyGeo already has a lot of GNNs built in, so you can play around with them in 14 lines, as is shown here. And then to train them, you use a normal PyTorch training loop. So there's nothing really too hard to get started with graph neural networks, and it's a lot of fun to try out. Now, on top of that, I've started to use PyTorch Lightning, following the example of the Exatracks group. So Lightning is a layer on top of PyTorch that aims to make your life easier. So first of all, it cuts a lot of boilerplate. So for example, this training loop that we just saw, you don't have to write that anymore. You don't have to remember to zero grad. You don't have to remember to put the no grad decorator for your validation step. A lot of these also beginner mistakes are kept from you. But at the same time, I think it's quite easy to open kind of hatches anywhere if you want to really tweak something back to normal PyTorch level. So on the right, we see how this looks. So this is an example I picked from the documentation. So this is now a Lightning module. Again, you initialize a model or layers in your init method, but there's already one special call, say hyperparameters, that takes all the input arguments that you have in your init method and puts them in a dictionary self.hparams. This can be really convenient if you have 10 parameters here. You don't have to self.whatever equals something something for 10 lines here. And also the self.hparams thing will become quite important to track hyperparameters. The downside, of course, is that it's going to mess with static type checking. basically you won't have static type checking with the magic of safe hyperparameters. So that's a bit of a trade-off. But anyway, you got your model initialized. You put your forward method here just as before. And now the new thing with Lightning is that it puts this training step and validation step together with your module. So here you take you describe what happens to one data element. So for example, with the training step, you would basically just call forward on the model and then calculate the loss function, and then Lightning will do the rest for you. And for the validation step, you would explain to Lightning how you calculate your metrics of choice for one batch, one single graph, for example, of your data. And now training it also, it's basically just 2 lines because you don't have to write anything yourself anymore. But I wanted to point to a really cool thing. After you've trained it and you've saved a checkpoint, you can restore the whole model with a single line with this load from checkpoint class method. And that's really cool because it also takes care of your hyperparameters here. So you don't have to first initialize your model and then load the state dict or the weights, but it's really just this single line. And this can be used to restore quite complicated classes that you build up here. Now there's hooks for basically anything, which can also really help to make your code more modular. If you have several different models or pipelines that you're training, and you have tweaks that are common to all of them, it's really easy to put them in a separate function or class. And Lightning is really good at managing hyperparameters and restoring models. That's what we just talked about. And this includes that all the hyperparameters can be initialized from a YAML file, and they will be saved to a YAML file. And you can always tweak them from a command line interface. That's really useful. So what I didn't like at first, and a little bit of a wall of text. So you always bundle this model architecture, or in the way it's laid out in the normal tutorials, with your training and validation step. And that can be less elegant when you're dealing with a lot of different model architectures that you use to solve the same problem, because you just don't know which architecture works well yet. So, one way would be to just add even more hyperparameters here to parameterize over all of the different models. Well, there's a bunch of different ways you could approach that. But what I instead did, and this is kind of departing a bit from the usual Lightning paradigm, and we can talk about if that's a wise choice, I instead went with more or less normal PyTorch modules that I then pass in as a parameter to a Lightning module, which then has the train and validation step. And in this way, I can just use multiple PyTorch modules that I can just plug in here, and all the rest of the training validation infrastructure is the same. So the problem is hyperparameter management, basically the big selling point of Lightning for me anyway. And for this, it doesn't come pre-built. We basically now have to recurse into the hyperparameters of the model. So for this, you also inherit from hyperparameters mixin that's provided by Lightning to have this build up the self.hparams dictionary. And now I wrote a function that basically makes sure we do the bookkeeping to basically add the hyperparameters of the model to the hyperparameters of this whole Lightning module here. And also vice versa. If we initialize some hyperparameters, it means that this thing will be called with just a dictionary of hyperparameters, and we need to get the actual model back. So the way this is done, and this is kind of what this function looks like, is if we are being given an object, we kind of serialize it, as in we remember the class path, like where was this model imported from, and the initialization arguments. That's done with this hyperparameters mixin magic. And in the opposite case, where this is currently being initialized from hyperparameters, we restore the object from the class path and the init args. So this was a lot of fun figuring all of this out. I don't know if there's a better method. I personally think this should just be kind of built into Lightning, because it's also very useful if you have nested modules, if you have modules that take submodules and you want to combine the hyperparameters. I'm planning to write a separate tutorial or package for this soon, but it's basically just like 200 lines of code. I've linked it here if you're interested in it. Second thing, and I'm close to the end, not sure how I'm doing time-wise. Weights and biases was also very instrumental in driving this project further. So this is basically a dashboard to track your machine learning runs, especially if you have different hyperparameters with them and you want to find out what works best. You can also track model lineages and more. It's not open source. There's, I think it's MLflow. There's open source alternatives. I think they're definitely less pretty and not as nice to navigate, my personal opinion, but they are working. So kind of pick your poison situation there. Another recommendation that is independent of that, there's a package called cool names, where you can generate random cool sounding names for your ML runs, which is really cool to remember, like models, because like if you just have abstract hashes, that's really hard to keep track of. If you, for example, found a model that works really well and you want to come back to it. And it's also really fun if you discuss with people and you talk about the original spectral hound or the kind bald hamster. So the cool names package is absolutely great. So the only thing with weights and biases is it needs internet to synchronize, because it's a cloud application, you can't run it locally. And then on many academic HPC clusters, you, for example, have Slurm. So you, in order to get your big GPU, you submit a job and you get a worker node, which oftentimes is not connected to the internet. So this is shown on the picture on the right. You have your own laptop, you SSH to your login node, then you, for example, run Slurm, and now you're down in a worker node, but it doesn't have internet connection. But this is now where kind of the weights and biases hooks runs, and it can't talk to its cloud. So the way to solve this is you set it to offline. It writes to the shared file system, and then later you can manually call vendb sync and tell it to sync. But then it's kind of, you lose a very nice feature that is having kind of seeing the live progress. Or you do something like you constantly loop over all of the saved runs and call the synchronization and so on, and it's not going to be very elegant. So I wrote a package called either that or some abbreviation of that. Anyway, this is the GitHub link that basically leverages, if you have a shared file system, it's going to communicate through that and always tells the head node when to sync which directory, because something new has happened there. So you basically get back quasi live synchronization. So this is summary. Having slides from other presentations to recycle for emergency last-minute talk preparation is a lifesaver. That's my personal takeaway message from today. But back to topic. Learned clustering or object condensation is another machine learning approach to tracking. Edge classification is the most studied one, and it works really well. With learned clustering, I think we have very promising results, but it's still some time until we know for sure. If you want to play around with something like that, there's open generic detector data for the HLHC pileup conditions. This is the TrackML data set. You have to be careful. There's two versions of it, one on Kaggle and one on CodaLab. The CodaLab one is the one you should use because it has bug fixes. there's currently some issues with CodaLab, where you can't create some accounts, and it's hard to get this data, so you have to write people, and they should fix it. PyTorch Lightning is helpful for beginners and experts, is my opinion. Weights and biases is one option to track your experiments. I think the only thing is there's better things than a homebrew system of having hundreds of CSV files on your disk that you load in Jupyter notebooks, because having these interactive dashboards is really nice. And this VanDB OSH thing that I wrote helps if you run into this offline synchronization issue. Now on the right side, there's some more links. We have this GitHub organization. We do actively look for new contributors. So if you're interested, let us know. There's also a separate repository with tutorials, which probably work. I wanted to update them and make something hands-on, but it didn't happen. There's a more in-depth talk tomorrow at Connecting the Dots. Lots more people on the slides and lots more details about the performance and the physics of it all. And I also wanted to link to another big repository from Exotracks. We've been working on this problem for way longer than I have, mostly with the edge classification approach. They also have a public repository. They don't develop it completely public because they have a separate repository, but there's some really nice stuff there. Now, I don't know how we're doing with time. I could very quickly show.
I think, unfortunately, we're basically a few minutes overtime at this point. But
oh, shoot. Sorry.
Oh, you're fine. Yeah. But maybe you could just say what if you had some examples, maybe you can tell people where they should find them.
Oh, it's all on the GitHub. It would have just been like
great.
an example of a config file and showing the class path and init args and how they appear here. Not too important.
Okay. Well, we should probably cut it off here, but thank you, Kilian, for this very nice talk. And also, if people have questions, maybe they can ask them on the Monday session 2 Slack channel, and there Kilian can try and give some follow-up in the future. And also, if you are around and available, check out the Connecting the Dots talk tomorrow, which should be quite cool. So yeah, thanks very much, Kilian. And then